So yes, you would expect that MPI creates a separate thread, but actually most MPI implementations don't do that. So so what they will do is when they do a non-blocking send, they will actually try and send the message if there's a receive. If there isn't a receive, they will sometimes maybe just send a notification to the other process saying I have a message waiting for you, and then return to you. So because there is no extra thread, that message can't be sent until it next enters the MPI library. So most MPI implementations do not spawn extra threads; they're single-threaded. And what they do is they use every time you call an MPI routine, the first thing they do, if you call an MPI send, the first thing it will do is say, okay, he wants to do a send, but I'm not going to do that. I'm going to check. It will use it like a manual interrupt to go and check everything else that is going on. So there will be minimal overhead. However, it may not be dealt with in the way you think. It may not actually be delivered in the background because MPI isn't running all the time. MPI is only running when you call an MPI routine. However, it does mean that you avoid deadlock. Does that make sense? I mean, if MPI were designed today, then probably it would be more thread aware. I mean, there's nothing to stop MPI doing what you suggest. And some MPI implementations have the option to do that. Like on the Cray, there's a way of running it to say, I would like you to spawn an extra thread. But no, I mean, no, basically, well, I don't know quite what you mean. But, the other thing about you did spawn an extra thread, what you might be able to do, and this is a hope for the future, is that you would run your MPI process on. Remember, we normally have hyperthreading, and hyperthreading only works if the two threads are doing different things. Well, they are here, so the hope is you'd have one process running on the first core, doing your main program, which makes MPI calls, and the second process or thread, which is progressing, which is dealing with the MPI calls, could run on the same physical CPU but on the different hypercore, and so they wouldn't actually interfere with each other. But every time you call an MPI routine, the first thing it does is it does other stuff. It goes around and checks if there's anything else going on, any non-blocking sends or receives to process, anything it needs to do, and then it will process what you asked it to do. So it's not even as sophisticated as callbacks. I think it really is just, the first thing when you call the MPI routine, if you looked at the code, the first thing it does is I will go and check and progress everything else, keep everything else moving on. Does that make sense? I mean, you can look at, I haven't read it, there is a discussion in the end. Are you at a university? Are you a student or a staff member, or? I mean, do you have access to a university library? So definitely so you're doing gaming, are you? Games programming? I know that's HyperThreading's big USP. Oh, okay, you're not. Okay, fine. Oh, that's interesting. Okay, so definitely at the moment, okay, that's interesting. At the moment, for example, I'll show you something here. Let's just, what's going on? Oh, that's not what I wanted to do. I've shared, you can see what I've done, can't you? I've shared my so so what I'm trying to show you here, I noticed the other day is grop MPI. So so here's the using MPI portable programs. So this is the book I recommended, but at the moment, for a short time, there seems to be free online access. So if I now I don't know if that happens for your university, but if I go to the online access and then I have to sign in, but I can use my university login to sign into wherever it goes. It just depends whether your university has a subscription, but they're offering it. Oh, why didn't that work? Oh, full text available here. Sorry. So I noticed when I was looking. So now there is it's available online. Table of contents. So there is a section here, understanding how the MPI implementation works, which talks about. So I don't know if you have access to this book, but if you're interested, yeah. So it talks about how it does sends and receives and non-blocking and different protocols and such like. So I mean that's I mean the online access seems to be temporary because of COVID, but I don't know if your library. That's just when you can buy the book. I don't think there is an online PDF. Remember, I don't think there's an ebook. I don't know, but anyway, if you're interested, you may be able to get it through your university library. And it talks there about implementations and such like, which might be. I mean, I haven't read that chapter. All I know is from speaking to people that have worked on it, so that might be useful. The other thing I should say, I don't know if I'm pronouncing your name rightly, Naman, is that you're talking about cluttering the CPU and scheduling. Although when you run multiple processes on a shared memory computer, the way that the processes are allocated to CPUs is up to the operating system. So actually, on a dedicated high-performance computer like Archer or Archer 2, the job launcher, the equivalent of MPI run, will tell the operating system to pin the processes. So it will say, on Archer, for example, we have 24 processes we have 24 CPU cores per node. It will say, if you run 24 MPI processes, it will pin rank 0 to CPU 0, rank 1 to CPU 1. So this thing I said about if you had a helper thread, it would hopefully be pinned to the hyper core of the physical core that it was of its parent process. That would all be done by the launcher program. So the MPI run program would do all that for you. So on your laptop, you'd have to kind of do it by hand probably, but on a dedicated supercomputer, these things will be all this stuff about physical, where the process is physically run, will be set up or managed at the MPI at the launching stage. So you're saying using ultrasound results, I just wonder what opportunity would be best for real-time interaction with the user. So I mean, for real-time interactions, the problem with HPC systems is that they're not set up for real-time interactions. So, well, because you run via batch, so you submit a batch job which might not run for 3 or 4 or 6, 10 hours. It might run at midnight. So I mean, you do have interactive access, but it's quite, and then again, it's not easy. Well, it's never easy to get the compute. Remember, you only access the compute nodes via the login node. So if you want a external user to interactively manage an Archer job, it has to go from the user to the login node to the compute nodes. That's always been a bit tricky, but with the extra security levels we've had to put in because of the recent security incidents all over the world, I don't know. I mean, what kind of interaction is it? What is somebody doing? Are they selecting parts of an image, or are they doing visualization, or what? Oh, okay. Okay, I see. I mean, there are ways of doing that. Archer or Archer 2, maybe not the best platform. Something like, I mean, Cirrus, which is I mean, if you know when you're going to be doing it, you can submit a reservation. So you can actually submit a job which says, I want this job to run between 3 p.m. and 4 p.m. on Tuesday afternoon, and it will schedule it for then. So you can guarantee access in that way, although it's for a time-limited period. But I would have thought that Cirrus, which is one of the the tier 2s, so Archer 2 in the UK terminals, tier 1 systems, the largest systems. There's also a range of 8 or so national systems, but smaller tier 2, of which Cirrus is one of ours. We've got 10,000 CPU cores. It's currently not in service. It's being upgraded with a few hundred GPUs, but something like Cirrus would be definitely more flexible. I mean, because you'll want to open sockets and things like that, and all that's potentially quite difficult on Archer, but much more likely to work on Cirrus. So I would say Cirrus. Let's see if we can give you a URL. So that's the Cirrus URL. So there are other tier 2 sites. If you want to see all the tier 2 sites in the UK, you want to go to this, but so is there any way to partition unstructured grid with flexible number of processes? I may wrong graphs only how could you write the program for a fixed number of? Well, yes and no. I don't understand, because when you run, so the graph topology is so I don't quite understand your problem. So you have an unstructured grid. You can partition it, for example, using Metis or something. I mean, you typically partition these. Well, I don't know if you want to. So this, yeah. So there's a bunch of stages. So for example, for a structured problem like the case study, it's easy. It's trivial to partition a regular grid into slices. For an unstructured problem, it's much harder. So typically what you do is you use a package like Metis, some unstructured graph, some graph partitioning algorithm to tell you what the decomposition is. So you could do that as a pre-processing step or within your program, but you call something like Metis and it says these elements belong to these process. Rank 0 should have elements 1, 5, 9, and 23, and rank 1 should have elements 2, 6, 15, and then I don't understand what the problem with the graph topology is. So, but when you run your program, you are running on a fixed number of processors. You've run it on 100 processors, and you define the graph topology within that program run. So you define it on 100 when you're running on 100, but there's function calls. I don't understand. Sorry, I'm not being silly here. I don't understand your question, really. I mean, you write the code for a fixed number of processes. In some sense, that's a variable, that's size, which is determined at runtime. So I maybe don't understand what you're asking. You can use audio if you want. It's sometimes easy. That's for Lee. It's sometimes easier if it's up to you.
Yeah.
I am recording the audio if that's okay.
Yeah, David, can you hear me?
Hi. Yeah, sure.
Yeah, so for example, if I partition my domain into like four partition,
yeah,
then in the runtime I can't change it into 5 or 6, right? Because the code is written in such a way that it can only run in 4 partitions. If I use the graph topology. What?
So you talk about the MPI graph topology, or?
Yeah, the MPI graph topology.
But that's defined at runtime, so you can define it on whatever number of processes you're running on.
Oh, that I may be wrong. Okay.
So I don't understand the problem. You're right that you have to partition your mesh into the number of processes you're running on. So if you want to run on 23 processes, you have to rerun metis to decompose it into 23 pieces. But once you've done it, I mean, all you pass the graph topology is effectively the identical information you get from to define a graph topology. You just say which processes are neighbors of which processes, which is going to be an output from metis in some sense.
Okay. So if I'm to like partition the unstructured grid, do I have to use the metis that you mentioned?
Well, it's up to you, but you have to decompose the unstructured grid, and if you decompose it well, it will lead to a small amount of communication. If you decompose it badly, it will lead to a lot of communication. Yeah, you want all the elements which are next to each other to be on the same process, so that you don't have to. You have to basically swap information between neighboring elements in a standard finite element scheme, I guess.
Yeah.
Or any finite volume. Yeah. So if neighboring elements tend to be on the same process, then that doesn't require communication. So you want a decomposition, which means that the majority of elements which are neighbors end up on the same process. Now you can do that however you like, but there are packages like metis which do it for you.
Okay. Thank you very much.
You could do it randomly. You could say the first 100 elements are on process 0, the next 100 elements are on process 1. That would work, but that could lead to a huge amount of communication unless you're careful.
Okay.
But do you have a code, a serial code, a parallel, anything? Do you have anything? I mean, I don't know what stage you're at, and what kind of simulation you're trying to do. Fluid dynamics.
It's a 2D Euler equation code. So I use finite volume, not finite element.
Okay.
Yeah, it's unstructured grid. And I have the serial code. I'm trying to parallelize it. It's just I don't know where to start because it's unstructured.
Yeah, so unstructured is a lot more challenging than structured. I mean, in principle, it's the same. Yeah, in principle, what you do is you have halos. You know each I guess in the finite volume method, each element, or I don't know if you call them elements, voxels, I don't know what you call them, but needs to talk to all its neighbors. Yeah, so you basically do the same as you do in the structured case. You have an initial halo swapping phase where you bring in all the elements that you need, and then once you've communicated them, you can then do the calculation locally because you know all the data you need to know. It's just the bookkeeping in the unstructured case is a lot harder because it's unstructured. So conceptually it's the same process, but implementation wise it's a lot more effort. But I mean, yeah, so I mean, are there not packages that do these things already? I would have thought, there are a lot of packages out there that do this kind of thing.
I don't know, I'm not familiar with that, but I will have a look on it.
Definitely try and look for an existing. I mean, there are packages out there, things like Phoenix is one that's for finite element problems, where you're solving a linear system. Are you doing time evolution, or are you looking for a
time
solution?
evolution?
Yeah, okay, so that's different. So, but I mean, I would definitely look for a package which does what you want. I mean, writing, a parallel unstructured finite volume solver is technically quite difficult. I mean, it's just involved. It's just, a lot of bookkeeping. I mean, how many processes do you want to run it on? 10, 100,000?
No, it's just a simple code. I just want to parallelize it, just like do some hands-on on it, just a practice. So it's not
well,
yeah.
I mean, I think, as unstructured problems are very difficult to, it's a very, very hard thing to do. I would definitely program up a structured problem first, and then move to the unstructured.
Okay.
I mean, if you need to parallelize it on a modest number of processes, OpenMP might be a lot easier, which is only works on a single computer. So, for example, if you had a server with 10 CPU cores or 20 CPU cores, you could run on up to 10 or 20 CPU cores, but it'd be much easier to parallelize in OpenMP than in MPI. 10 times easier. I'm a lot easier, but you would only be able to run on a single shared memory computer.
Yeah. Okay. Thank you very much.
So yeah. Okay. There may be people out there who have written example. Are you C or Fortran or C++ or what?
Fortran.
So I just did a Google search, and there's things like this, what did I Google for? I can't remember what I Googled for. Open source 5.1 fluid dynamics code, a free high order solvation power module. I mean, that's maybe something. I know there's stuff out there, if you, I would definitely look at what you want to do is you want a framework which is already implemented, the framework, the parallelization, the decomposition, and then you can just adapt it and stick your particular equation or particular whatever into it. But writing it all from scratch is quite challenging. Does that make sense? So there's a question from, apologies if I'm getting the name wrong. Is there a way to spawn new process at runtime? Yes. So you can do it at something called MPI com spawn, but it's really not a good idea. I mean, it's hard to think. So the reason it doesn't make any sense. I mean, you can do it. Some MPI implementations support it. There's something called MPI com spawn, but the way, if you're running a large-scale parallel program, you submit it via a batch system, and you submit a job, and you say, I want 2,000 processes for 10 hours, please. Okay, and then maybe next week your job runs. You've got those resources. You've got to use them. Resources do not become. If you need more compute resources, then you had to have requested them from the start. So you would have run on all those processes anyway. I mean, you can choose to run on few. I mean, you can basically say, if you have 2,000 processes, you could just say, if rank is greater than 1,000, do nothing. But I mean, you're paying for them. So HPC systems don't allow you to get more resources because they're not dynamic cloud-based type things. You got 2,000 CPUs for an hour, you got to use them or not. So although you can in principle grow and shrink MPI, it's not any use because there is never a situation in which you can actually ask for more processes. Do you see what I mean? You need to say, oh, my program now needs more processes. So it was a big, when grid computing was a thing 15 years ago, it was a big, but it doesn't make any it doesn't fit into HPC. That's more of a cloud type concept. And if you're programming in the cloud, you wouldn't use MPI. So yeah, it's a good question. It is supported, but it's very awkward to use and not particularly useful in practice. So can what be useful for load balancing? I guess I doubt it would work though. I mean, you'd have to, the problem is your MPI program can launch more processes, but you'd also at that point have to tell Azure that you needed more resources. And I don't know how you're going to do that from a running program. Do you see what I mean? You're going to have to, it's going to be awfully complicated to do. So yes, a cloud service could give you more resources at runtime, but you're going to have to request them from within the MPI program. And I don't know how you do that. I mean, maybe you can do API calls and things, but it all sounds horrifically complicated, I have to say. I mean, MPI doesn't fit. The model of MPI is you have a fixed number of processes for a fixed time and you run on them. Because it has no fault tolerance in it, no timeouts, no nothing. Whereas the cloud model is much more, well, maybe it isn't for HPC, but yeah. Yes, in principle, on a cloud model, you could request more resources and then grow to fill them. But I wouldn't do that with MPI, I have to say. I think it would be too much effort. And I said I don't quite see how you do it technically. I might be wrong, but I don't immediately see how you do it. So I mean, young people, not old people like me, do see MPI as being quite old-fashioned. It is quite old-fashioned. It is quite an old-fashioned model. But then HPC is quite an old-fashioned. Obviously, it uses leading-edge technology. And what I mean by old-fashioned is it's not dynamic, it's not fault-tolerant, it's not Web 3.0. It's basically, here's 2,000 processes for 2 hours. Off you go. So that which is not a model. Which is not the modern model for computing, really distributed. But then we buy large supercomputers and put them into resources and put them in supercomputer centers, so they are there. Maybe not a very good answer.